Okay, welcome back. Happy Wednesday. Glad you guys made it okay. I think we'll probably have a few people straggle in because some of the roads were pretty bad out there this morning. So today we are covering systems of equations by algebraic methods. Last class we solved a lot of systems of equations by graphical methods. That is just intersecting two lines, right? So we had systems of equations, which were these two different equations. We drew two lines. We found the point of intersection, and we said this point right here is the solution. So today we're going to talk about solving those same kinds of problems, but we'll use algebra. Doesn't rely on any graphical anything. And then coming up on Friday is our first of 2 days on applications of these systems of equations. So the second of those days is Monday, and then Wednesday we have our review day for test number 1, which is coming up on Friday. So a couple of differences between tests and quests. Number 1, tests are worth more percentage-wise. I don't remember what they're worth. You can check out in the syllabus, but they're just weighted more heavily in your grade at the end of the semester. But also the tests are on a lot more stuff. Essentially, this test coming up a week from Friday is a midterm. I'm not calling it that. It's one of 2 tests, but it's roughly the middle of the semester, getting there anyway. And it is on everything from the semester, classes 1 through 13, whereas the quests are on maybe like 4 or 5 classes. Tests are on a lot more. So first test is coming up. It is not too early to start studying for that test. Again, you've got on the left hand here, this column C, all of these practice problems that you can use to help you prepare for that test, all right? But it's going to be on everything. You don't want to wait until the day before to study for this essentially midterm. Okay, and then next week is our last full week before spring break. So that Friday will be the last day before spring break, and then you guys will go off, and then we'll come back after that. Questions on the calendar? All right, so then again, on page 77, we'll jump up here to the top. Daily summary, Lucas.
In this lesson, we solve systems algebraically, not graphically, which is what we did previously. In 2 methods, substitutional and elimination.
Okay, thank you. So the first method we're going to talk about is this thing called substitution. So we're just going to run through this quickly. The demo here is a little bit long, and I just want to get through it fast so that you have a lot of time to practice in the activities. But here's this new system of equations, which we're going to solve. Again, last class, we would draw those 2 lines, intersect them roughly, and then say that's the solution. So today, no graphs, just algebra. So the first step is we're going to solve either equation for either variable. Now there's some hints in here that you can read later on as to decide which equation you should solve and for which variable. If you want to solve the first equation for x, or the first equation for y, or the second equation for x, or the second equation for y, you can do any of those 4 things. In the demo here, I'm going to solve the second equation for y because there's no number in the front of the y, or I guess there is, it's an invisible 1. Turns out it makes it a little bit easier, but you can read that hint later on. So solve this guy for y by subtracting the 4x from both sides. Yeah? So everybody believes that? Y is equal to 5 minus 4x. And then we're going to take that y and we're going to substitute it into the other equation. Which equation did we just solve, the first or second? The second one is the one we just solved. We're going to use the other one now. We're going to take that y right there, and we're going to change it into a 5 minus 4x, because they are exactly the same as each other, yeah? Y is exactly the same as 5 minus 4x. So that's what's going on here in this next line. I'll draw this here. So that first equation is copied term for term, except for the y, which got changed to a 5 minus 4x. Everybody see that? 6x minus 2 times 5 minus 4x equals -3. Notice the parentheses there. Got to have those parentheses because this y was one entity, and even though it's represented as 5 minus 4x, which is 2 things, it's still one entity. Okay, and so then we get an equation here that is familiar, that is solvable for us, right? How many variables are in that equation? Just 1, which makes it a whole lot easier than the 2 equations we had up above, which both had x and y. So you solve that going through the normal process. First step is distribute that 2, right? So I'm not going to go through the details. It's written out here. It turns out x equals 1/2 is what you get when you solve that equation. Now remember, when we're solving for a system of equations, we get that point of intersection, and it has 2 coordinates. It's got an x and a y. We just found the x. So we're not quite done. To find the y, you take that x equals 1/2. You can plug it into any of the equations on the board that has x and y in it. Turns out the easiest place to go is this one that says y equals. So we just plug a 1/2 in there for that x. So 5 minus 4 times 1/2 is the calculation for y. So I think that's 5 minus 2 or 3. So that's written out here. And we end up getting, like I said, 3 is the y, and so then our solution is here, a half and 3, or written as an ordered pair, 1/2, comma 3. Okay, so just running again through the highlights of this process. Solve either equation for either variable. This is the stuff in bold. Substitute into the other equation. Solve that new equation. It's only going to have one letter in it, like just x in this one. And then once you solve that, you substitute into the other, substitute to find the value of the other variable. That's the process in a nutshell. It's called the method of substitution. And of course, you can always check to make sure that your point works. So taking 1/2 and 3 and plugging them into both original equations, you end up getting true statements. So that's our way of making sure that we did it right. Any questions on the process? Like I said, this was a little bit quick. It's going to make a lot more sense to you. It'll be more meaningful to you when you actually do some practice. So the other main idea for today is this thing called the elimination method. And I want to go to the next page now. And we've got a brand new system of equations here. So we're starting over with a new system. And I'm just going to jump us ahead to, I want us to focus on the second system in part A right here. Okay, so just look there. Suppose that you add those two equations up, just straight up and down, vertically. What happens when you add the x's? You get 0. How many y's do you get when you add those guys? 27 y's. And then 108 minus 27, I don't know what that is, 81? I think it's 81. So what do we have? X's disappear. That's a 27y is equal to 81, which is an equation that we can solve very easily, right? So something really nice happened. What made it so that adding these equations here was nice? X is canceled, right? That was like a small miracle, but as soon as it happened, the rest of the process is going to be pretty easy. So the question is, how do we get from this guy where the x's don't cancel, right? That's 15x there, that's 1y, it's nothing cancels. How do we get from that to this really advantageous place where the x's cancel? So what we're going to do is we're going to multiply the whole top equation by some number and the whole bottom equation by some other number to put us in a position where the x's cancel. And so just take a look at this 9x and this 6x. 9 and 6, what's the smallest number they both go into evenly? It's 18. Everybody see that? I mean, you could do 9 times 6, which is 54, but it turns out it's easier if you can find the smallest number they both go into. So 9 and 6 both go into 18. What do I need to multiply the 9 by to get an 18? Is it 2? But you can't go around just multiplying the 9 by 2. What you're allowed to do is multiply the entire equation, both sides by 2. That's okay. And that's what we do here. Multiply that whole top equation by 2, everything, both sides. What do I need to multiply the 6 by to make the 18? Is 3. But we really like the fact that when we added these guys up, they canceled, which meant one of them was positive and one of them was negative, right? That's what made this work. So how about we multiply the bottom equation by -3? And so that's that -3 right there. So both sides of the first equation by 2, both sides of the second equation by -3. Lots of distributing happening here. That's 18x, that's 12y, and that's 108. That's there. And then on the other one, minus 18x plus 15y equals minus 27. That's there. And then the rest of the process is pretty straightforward. Add the two final equations. The x's disappear because we built them that way. And then you solve for y, and you get y equals 3, and then you plug in to find the value of x, and it's all pretty straightforward from that point. Okay, quick pop quiz here. What if you wanted to get rid of the y's? I've got 6y and I've got -5y. So don't say the answer out loud, but feel free to talk with your neighbors. What do 6 and 5 both go into? And then what can you multiply each equation by, two different numbers, to make it so that those y's will cancel? So talk to your neighbors, figure out what numbers would you multiply both equations by to get rid of those y's. Okay, we're just coming up with something. All right, so what's our answer here? First equation by 2.
Oh, sorry, I was still thinking another one.
First equation by 5, right? Because that'll make a 30y. Second equation, somebody else? 6, because that will make a negative 30y. Everybody see it? The process will look a little bit different. Not surprisingly, you'll get exactly the same answer for x and y at the end. So it makes no difference whether you eliminate the x's or the y's. You can do either one. You'll get to the same place at the very end. All right, so that's called the elimination method. So we had 2 methods today, substitution, and then the second one is elimination. I need you to be good at both of these things. And the reason that I need you to be good at both of them is that sometimes a given system is really easy to solve using one of these 2 methods, but much harder using the other. And if you pigeonhole yourself into just learning one, then you're going to make some problems much harder than they really need to be. Okay, and so I'm just going to be totally upfront here. On the test, there's going to be a problem where I say solve this one by substitution, solve this one by elimination. So you got to, even though they both techniques solve exactly the same problems, I need you to get good at both of them. Okay, let's go to Savannah for 5. You guys remember that? You drew 2 random lines that intersected each other. How many solutions in that case? 1, right? That 1 point of intersection. Then you had 2 parallel lines. How many solutions there? None. And then you had the same line twice. How many solutions there? Infinitely many. So those last 2 things are the special cases, parallel and the same line. So, okay, it's pretty straightforward when you're graphing these things to see if they're parallel or see if they're the straight line, but we're not doing any graphing here. So what we need to do is make sure we understand what to look for when we do the algebra that will tell us we're in one of these funny parallel or same line cases. So let's try this one here in part A. Okay, first thing says y equals 2x plus 1 and y equals 2x plus 3. We're going to do substitution here. So we're just going to substitute. Instead of this y right here, I'm going to put 2x plus 1. Everybody fair? Is everybody okay with that? Because y and 2x plus 1 are both exactly the same. So we can put a 2x plus 1 right there. Everybody see what we did? So that's substitution. And then what happens when we try to get these x's over on the same side? They'll cancel, right? Subtract 2x from both sides and they disappear. Well, that's a surprise. Okay, so what's left? 1 equals 3. With no x's in there to solve. Okay, we'll talk about it. Let's take a look at the second one. Again, we're going to do substitution. What we're going to do is replace this y right here with what that's exactly equal to y? 2x plus 1. Everybody okay with that? Because y is exactly the same as 2x plus 1. So I'm going to copy this equation, which is 6x. There's a minus 3. But instead of the y, what are we putting? The 2x plus 1. What am I missing? Okay, so we got the equals minus 3. That's true. But the parentheses. Whenever we do this substitution idea, we throw parentheses around whatever we substituted. Okay, so first everybody see where that equation came from? It's the bottom row, copied exactly letter for letter, number for number, except the y became 2x plus 1. Okay, so this is great because it has only 1 letter in it, right? Not 2 variables like before, so we can distribute there. 6x minus, so we distribute that minus 3, what do we get? 6x, and then minus 3, and then equals negative 3. And then what happens when we combine terms? The x's cancel, and we get minus 3 equals minus 3, which is another question mark. What's going on here? Okay, so the first thing is that we know we're in one of these special cases because the x's just disappeared. Normally there would still be an x left over and you'd solve it and you get x equals some number. But if the x's all disappear or if the y's all disappear, every variable disappears, then we're in one of these special cases. It's either parallel or same line twice. So let's go to 7. Ben, could you read 7? Okay, so again, the big conclusion, if it's false, then no solutions. If it's true, infinitely many solutions. So what about this part A right up here? We got 1 equals 3. No solutions. What did it look like graphically if we had drawn the two lines? There's two parallel lines. It's exactly what we would have seen here. So our big conclusion, no solutions. Because 1 equals 3 is a false statement. But in part B, the conclusion here at the end was -3 equals -3, which is definitely a true statement. So what's the conclusion here? It's infinitely many solutions. Infinitely solutions. Okay. So those are the two special cases.
Which is basically confirmed.
Yes, yeah, so in part B, the picture was the same line twice, right? And we confirmed it without drawing any pictures. So this is the algebraic way to know when are we parallel, when are we the same line twice. Questions on that? Okay, so the activity starts on the next page. I want to say one thing about the activity, but first, on your table, make sure you grab one of these pieces of paper. I put them on every table. Some folks were asking me, when is assignment blah due? And I would always say, I have no idea. But I decided to go in and copy and paste all these deadlines here for you. Okay, so if this helps you, throw it in your notebook someplace. It tells you when each homework assignment is due on my math lab. Questions on this? Okay, so here's what's a little bit unusual about the activity. All right, first of all, it's pretty short. So you're going to spend most of the time doing the even more practice. So there's a bunch of steps though for each problem, so make sure you do all of them. You're going to write a system of equations. You're going to solve the system using elimination. That's one technique. You're going to solve that same system using substitution. So you're going to solve the same system 2 different ways, right? Of course, you're going to get the same answers, but I want to see you practice both ways. And then you can check because I've given you the graph here. All right, raise a flag if I can help.